Hello everyone. In this set of videos, we are going to take a look at a topic that is related to the transfer of data across different parts of a computing system. In particular, we will be talking about DMA or direct memory access. And essentially what the kinds of things that we need to understand over here are, why do we want to sort of offload these bulk transfers? What are bulk transfers? When do we want to offload them? When does it make sense to use some kind of a direct access to memory and sort of free up the CPU? Right. Along the way, there is also an important concept called cache coherency that we need to understand a little bit about. And of course, along the way, we will also talk briefly about the AXI DMA engine, which is basically an IP block that allows us to make use of DMA kind of transfers within the context of a larger system. Now, in this set of videos, I will primarily be talking about, well, the more theoretical aspects of DMA, because the practical aspects in terms of actually measuring the kind of performance improvements that you see when you use DMA require fairly accurate timing measurements in terms of how much time it takes to transfer data from one set of memory locations to another or from memory into a stream. And this is not easy to emulate using Renode because Renode uses different clocks for the processor and for the hardware or the RTL, right. So, we will of course be looking at some of this in the actual hardware demos as in when the lab, and we do this in the lab context. But for this, the present scenario or these present videos, I am going to be focusing mostly on explaining them and hopefully conveying the basic ideas behind why we need DMA and how we make use of it. So, broadly speaking, the goals of our video set of videos for this week are to understand the concept of direct memory access DMA and its benefits, right. A little bit about how we configure the AXI DMA controller, in particular what are the kinds of register map that it has, how we need to allocate memory in order to use it with AXI DMA, and so on. Using coherent DMA buffers, which is basically allocated to the memory management in Linux, and this basically comes into play when we need to understand how to handle cache coherency, right. And ultimately, we will work out a couple of examples that will hopefully help to better understand the trade-offs between DMA versus direct MMIO AXI-Lite based transfers, and also when you might prefer to use polling, IRQs, DMA. Well, polling and IRQs are sort of two different ways of handling something. DMA handles a slightly different problem, but all of them, both the idea of IRQ as well as DMA, are essentially there for one primary purpose, which is to free up the CPU and allow it to do other work rather than just moving data, or in general to allow it to do work that is not just keeping it busy looking for something to finish. So, let us start by quickly just recapping what a data transfer in the AXI-Lite protocol looks like, right. So, you should at this point be familiar with the signals that we have over here. We have a clock, reset, and so on. The important kind of handshaking that we are interested in is there is an address, right. This is the write address. Of course, what I am talking about over here is the write channel corresponding to the AXI bus. And within that channel, what we say is there is something called a write address. Along with that write address, which we have made sort of the correct value that we want over here, we also use another signal which basically says this is write valid. Now, strictly speaking, the reason why I can use a dark shade of gray over here is basically because until this signal valid becomes high, I really don't care what the values are over here. It's not that the values are at 0.5 volts or somewhere that the voltage is unknown. It is some kind of a digital value. It's either zeros or ones on the bits, but I don't care what those values are because nobody is looking at them until the valid signal becomes high, right? Which is why we basically draw timing diagrams like this, where we show that it's don't care in this segment and in this segment, but is valid over here. Well, it has to be related to the place where the actual valid signal is raised high. Now, the way the write address handshaking works is I can make the write valid, the signal address valid signal over here, and I need to wait for an address ready acknowledgement, right, which comes from the bus or the peripheral that I am talking to. Now, once you have done that, typically what happens is that peripheral then sort of says, okay, I am now ready to accept data, right? As soon as it gets an address, it sort of says I'm ready to accept data, although the protocol by itself doesn't necessarily specify that this has to be immediately followed by this. All that it says is you need to ensure that there is an address handshake, a data handshake, and then there is a response handshake that comes back, right? All of these have to sort of happen. All three states have to happen in order for one data to get successfully transferred across the bus. Alright, so now I have managed to sort of transfer the address. After that I say, okay, at this point in time I am actually putting the data onto the data bus. I also make the data valid signal high, and well, the peripheral that was supposed to receive the data has already made its ready signal high, so that's good. At this point on this clock cycle, the data transfer has happened, okay. And this be ready is something which I sort of, this once again is from the source of the transfer, right. I need to sort of make it high to say, okay, now once you have got the data, please acknowledge back to me that you got it. And that happens where the secondary, the target of the transfer, needs to basically make the be valid signal high, and the be response is usually just a 00 to indicate okay, right. In other words, the transfer succeeded, or it could say have an SLV error, slave error, something went wrong, the data transfer did not occur as expected. Now the point of recapping this entire handshake, which we have already seen in the earlier videos, is you can see that there are multiple stages involved. There is an address transfer, a data transfer, and an acknowledgement. Now if you tune it carefully, you might be able to sort of squeeze this down and maybe cut this down as much as possible. You could potentially have a design where the ready signal also goes high on the same clock cycle, so that the entire transfer occurs right here on this clock edge, and potentially on the very next cycle you could say, okay, the address and the valid need to go low. I could also say that as soon as that has happened, I need to sort of put the data. In other words, there could be some amount of fine tuning or tweaking of this waveform that you could get to try and reduce the total number of clock cycles that we have over here. Right now if you look at it, right, the number of clock cycles that are being used are 1, 2, 3, 4, 5, 6 clock edges for a single data transfer, right. It's not easy to reduce it much below that, but more to the but it can be done. I mean, some amount of squeezing could be possible over here. But more to the point, as you can see over here, the way that the data transfer works is, for every single value that I want to transfer, I need to basically have an address, then the data, and then the response, okay. It doesn't matter that the very next value that I am reading is from the next address, I still have to send that address, okay. Now think about what happens if I actually need to copy data from one set of locations to another set of locations. It could be, I have an array somewhere in memory and I want to just copy the data somewhere else. I need to first read, and I don't have the handshaking diagram for read, but it's almost the same level of complexity. It just doesn't have this acknowledgement channel at the end, right? Or rather, it's marginally simpler than the write because it has only 2 channels and not 3, but pretty much the same kind of handshaking that we have, okay. You need to read data, store it into some kind of a register somewhere, the temporary storage inside the CPU, and then do a store, right. So there is a load and then followed by a store, where the store basically does a write operation and sends it back out into another location in memory. I will also probably need to compute the addresses, the read address. I need to store it in some register, I need to then increment it to the next location. I then similarly do the same thing for the store address, right. So there is a store, there is a change address, or rather there is a load, change address, store, change address, and then repeat the entire thing, for which there will be some kind of a for loop, right, where again I need to sort of look at the for loop index, I need to decrement it. In other words, you can clearly see that if I need to transfer even just, let's say, 2 or 3 words from one set of locations to another, I'll probably take tens of clock cycles at the very least, right. So AxiLite can be used. It's a fairly good protocol because it ensures that the data is sort of transferred reliably, and it also makes sure that you can actually have like different speeds at which the memory is working and so on, and it will still take care of that, because the handshaking ultimately ensures that the sender and receiver are both synchronized properly with each other. But it doesn't seem like a great idea in the case where I want to sort of transfer large amounts of data or copy large amounts of data from one set of locations to another. Okay. So, we already saw one example of this in what we call the vector mode. In the FFT and FIR examples, what we did was essentially I had something where I would write something into the driver. Of course, over there things were even more complicated because the driver actually had to sit and parse data out, right? It had to sort of string to UL, so string to unsigned long, it had to parse the data out as integers and then go around writing data into the appropriate locations. Now, each and every one of those writes was a AXI-lite write transfer. It was done using a for loop. So, the address into which to write was being calculated each time one by one and so on. Okay. What that ultimately means is that even if somehow I magically did not have to parse and let's say all the data was already sitting somewhere in memory, I would still have taken several cycles per transfer of data, which especially in the case of microcontrollers which are running at hundreds of megahertz clock frequencies could very easily limit the bandwidth that I get to tens of megabytes per second. Okay. Now, what do I mean by bandwidth? It is the number of bytes per second that I can transfer. Okay. And this bandwidth is one of the key metrics that we use in order to find out whether we are doing some kind of a transfer or some data movement efficiently. It's not just that, the crucial point over here is right at the bottom. The CPU is busy during these transfers. What do I mean by busy? It's loading data, it's incrementing an address, it is then performing a store, it is again incrementing the address, it is checking the value of the counter, it is then performing a branch, right? During that time, basically for these tens of cycles for transferring each data that we have, the CPU cannot do anything else. Right? Now, there are scenarios where that is valid. You have a simple microcontroller, you don't want to complicate things, this is the only job the CPU really has, by all means go ahead and use this. But most of the time what we are interested in is we want to be able to do actual computations, something useful with the CPU, not just moving data around from one place to another, right? So, what we do in such a scenario is we bring in something called a new bus master. Okay. Now, what exactly is a bus master? This is a picture that we have looked at earlier, right, where we essentially have this notion of the bus. And what we said was there is this thing which is the CPU connected to it, and then what we have are all of these other things like the memory, the UART, the let's say the timer, right, smart timer or not, whichever way it is, all of these are connected onto the bus, right. All of these are what we call the secondary or slave devices, right, whereas this one out here is a bus master, right. So, what do we mean by a bus master? The CPU is capable of initiating transactions on the bus. It can actually start the transfer of data from one location to another, right. None of the others can actually do that. The memory block by itself is only there to respond to requests for memory. The UART can respond. If I want to transfer data out of the UART, I will basically write into it. If the UART already has data sitting in it, it can send an IRQ, but it cannot initiate a data transfer, right. It can send an IRQ and then the CPU needs to go read the data from the UART and then place it somewhere in memory. So, in other words, the CPU is the bus master. Now, what DMA does is it says, okay, let me add another bus master out here, but one who is not really programmable in the sense that I don't have an instruction set. I don't have the capability of actually running like loads and stores and adds and branches and so on. Strictly speaking, it can do loads and stores, but you don't call them loads and stores. All that the CPU can do is move data into or out of memory, right, or rather from one memory location to another. So, it literally lives up to its name, direct memory access. What it does is it can initiate a transaction on the bus. If necessary, it can basically pick up data from the UART and then push it into memory or the other way around. Okay. Now, typically the UART is a low speed peripheral. It happens so rarely and takes so little time, or rather so much time to perform each operation, that the CPU might as well just copy the data into the UART and be done with it. But let's say we have other peripherals like for example Ethernet, USB, the video system, right, the display. All of those require huge amounts of data to be transferred, and if the CPU is going to sit around transferring data, it's going to be busy all the time. So rather than do that, we allow the DMA to sort of take over and just transfer a chunk of data from one set of locations to another. It could be that we take it from, let's say, a video block, right, and basically say that from memory copy a frame of data into video so that it shows up on the screen. It could be Ethernet, in which case it basically sort of copies a chunk of data and then says, okay, now transmit this at 1 gigabit per second high speed. Okay. So the DMA, in other words, is doing one thing that the CPU can do, which is actually initiate transactions on this bus, but it cannot do anything else, right. So the DMA cannot, for example, perform computations, it cannot even do an address calculation on its own. All that it can do is transfer data. Okay. So it is another bus master because it can initiate transactions, but it also has a slave interface, right, on the same AXI bus, which basically allows the CPU to send configuration information to it or to program it. Okay, so the way that it works is the CPU can basically tell the DMA, this is how I want you to behave, and once that happens, the DMA then takes over as a bus master and coordinates transfers between the different peripherals. So of course, all of this sort of should tell us that the benefits of DMA are going to be higher throughput. How high is going to be hardware dependent. The CPU is now free during transfer of data, right? And what happens is that since we already know how to use IRQs, we will use interrupts so that the DMA can basically complete the transfer and then interrupt the CPU to go and process whatever has or rather to say, okay, what do I need to do next? So we will work through a few more examples in some detail, but as a sort of high level overview, right, you can sort of think of two ways of transferring data. One of them is using DMA, the other is using memory mapped IO, right. And DMA essentially we typically prefer it for large buffers. Now just like in the case of polling versus interrupts and so on, this number, what constitutes large, is very subjective. It depends on the bus speed, the processor speed, the amount of data, the bus width, lots of other parameters of that sort, right. Over here I put down a number saying 64 samples, but the point is that you need to actually check whether it makes sense given the bus speed, the DMA setup latencies and so on, whether it makes sense to use DMA or not. Okay. There is another place where DMA is often used, which is in the context of what's called streaming data, right. And the FIR filter is actually a good example of streaming data, because what we actually, the use case of an FIR filter is, I want to continuously send samples as and when they are received, maybe from an A to D converter, directly into my filter, right. And actually speaking, I don't want my CPU to be involved. I would rather have something which can read from, let's say, the A to D converter's register address and directly drop it into an address that corresponds to the FIR filter. And you could set up a DMA which does something of this sort, right, which basically says, okay, fine, I will have some kind of a buffer on the A to D converter, load a chunk of data into that, and then at one shot I set up the DMA so that it just takes a chunk of that data and very quickly, one after the other, sends the data off into the FIR filter, right. High rate peripherals, Ethernet, USB, video are all good candidates for using DMA. And DMA is also very often used when you have real-time constraints, simply because of the speed and latency constraints that we want to meet. Okay. Now, or rather the real-time constraints, meaning that we want something to happen within a bounded amount of time and probably at a repetitive rate. Okay. Now, MMIO on the other hand is typically good for small transfers. The example I am giving here is less than 16 samples. So if you look carefully, you will notice that there is a gap, right. I am saying more than 64 samples for DMA, less than 16 samples for MMIO. That is intentional. The point is, these are not hard and fast rules, right. So you need to actually check for any given problem, does it make more sense to use one or the other, and there will be some gray area in between where either one would be alright, right? If you go purely by the calculation of the latency, you might find that one is marginally less than the other, but it's so close that it really doesn't make a difference, right? In which case probably the simpler code might win out and say, okay, just use this instead, right? You might prefer to use MMIO because it's just easier to write the code for it. MMIO also makes sense when you have infrequent operations. You do not have to keep going through a setup process, right? You just have to perform a small amount of data transfer and then forget about it for a long time. You also want to keep your control registers simple, or you are just trying to configure simple control registers. That is to say, you are trying to write into certain memory locations, but the data that you are writing is probably something that is controlling something else, and you don't really want to do a bulk transfer of data, right? In the FIR filter, for example, the control status, all of those registers are things where you probably won't use DMA, right? You just sort of read them directly. But the data in and data out, it does probably make sense to use DMA because there's a lot of data involved over there. Now, this last part actually sort of relates to the constraints that I mentioned in the DMA case. Low latency, just like in the case of polling, very often we would actually prefer to use MMIO simply because the setup time, and this setup time has nothing to do with the setup and hold time that we talk about in the context of digital circuits. When I say setup time here, I mean the time it takes to set up a DMA transfer is usually fairly large, right? Depending on the CPU, depending on the bus speed and so on, it would be like several microseconds, possibly more, possibly less, but definitely non-trivial compared to the time required to transfer small amounts of data. So if you have really tight latency requirements, very often you will find that it makes more sense to just go with MMIO.